Differentiation under the integral sign is a useful operation in calculus. Formally it can be stated as follows. Theorem. Let f be a function such that both f and its partial derivative fx are continuous in t and x in some region of the plane, including a tb, x0, xx1. Also suppose that the functions a and b are both continuous and both have continuous derivatives for x0, xx1. Then for x0, xx1, this formula is the general form of the Leibniz integral rule and can be derived using the fundamental theorem of calculus. The fundamental theorem of calculus is just a particular case of the above formula. For equals a constant, b equals x and f equals f. If both upper and lower limits are taken as constants, then the formula takes the shape of an operator equation. It dx equals dx it, where dx is the partial derivative with respect to x and it is the integral operator with respect to t over a fixed interval. That is, it is related to the symmetry of second derivatives, but involving integrals as well as derivatives. This case is also known as the Leibniz integral rule. The following three basic theorems on the interchange of limits are essentially equivalent: the interchange of a derivative and an integral, the change of order of partial derivatives, the change of order of integration. Higher dimensions. The Leibniz integral rule can be extended to multidimensional integrals. In 2 and 3 dimensions, this rule is better known from the field of fluid dynamics as the Reynolds transport theorem, whereas a scalar function, d and d denote a time-varying connected region of R3 and its boundary, respectively, is the Eulerian velocity of the boundary, and d sigma equals nds is the unit normal component of the surface element. The general statement of the Leibniz integral rule requires concepts from differential geometry, specifically differential forms, exterior derivatives, wedge products and interior products. With those tools, the Leibniz integral rule in p dimensions is, where omega is a time-varying domain of integration, omega is a p-form, is the vector field of the velocity, I denotes the interior product. Dx omega is the exterior derivative of omega with respect to the space variables only and is the time derivative of omega. Proof of theorem. Lemma 1/2. Proof. From proof of the fundamental theorem of calculus, suppose a and b are constant, and that f involves a parameter alpha which is constant in the integration but may vary to form different integrals. Assuming that f is a continuous function of x and alpha in the compact set alpha 0, alpha 1 and xb, and that the partial derivative f alpha exists and is continuous, then if one defines may be differentiated with respect to alpha by differentiating under the integral sign, i.e., by the Heine-Cantor theorem, it is uniformly continuous in that set. In other words, for any epsilon greater than 0 there exists delta alpha such that for all values of x in a, b. On the other hand, hence phi is a continuous function. Similarly, if exists and is continuous, then for all epsilon greater than 0 there exists delta alpha such that, therefore, where now epsilon 0 is delta alpha 0, therefore, this is the formula we set out to prove. Now, suppose where a and b are functions of alpha which take increments delta a and delta b, respectively, when alpha is increased by delta alpha. Then, a form of the mean value theorem, where a less than c less than b, can be applied to the first and last integrals of the formula for delta phi above, resulting in dividing by delta alpha, letting delta alpha 0. Noticing C1 and C2b and using the above derivation for yields, this is the general form of the Leibniz integral rule. Examples. General examples. Example 1. The function under the integral sign is not continuous at the point e equals and the function phi has a discontinuity at alpha equals 0. Because phi approaches plus or minus bar 2 as alpha 0 plus or minus If we now differentiate phi with respect to alpha under the integral sign, we get, which is, of course, true for all values of alpha except alpha equals 0. Example 2. An example with variable limits. Examples for evaluating a definite integral. Example 3. The principle of differentiating under the integral sign may sometimes be used to evaluate a definite integral. Consider now as x varies from 0 to pi we have, hence, therefore, integrating both sides with respect to alpha, we get C1 equals 0 follows from evaluating phi. To determine C2 in the same manner, we should need to substitute in a value of alpha greater than 1 in phi. This is somewhat inconvenient. Instead, we substitute alpha equals 1 beta, where beta less than 1. Then, therefore, C2 equals 0. The definition of phi is now complete. The foregoing discussion, of course, does not apply when alpha equals plus or minus 1, since the conditions for differentiability are not met. Example 4. First we calculate the limits of integration being independent of a, but we have, on the other hand, equating these two relations then yields in a similar fashion. Pursuing yields adding the two results then produces. Note that if we define it can easily be shown that given I1, this partial derivative-based recursive relation can then be utilized to compute all of the values of n for n greater than 1. Example 5. Here, we consider the integral differentiating under the integral with respect to alpha. We have therefore, however, by definition, I equals 0, hence, C equals pi 2/8. An example 6 here. We consider the integral. We introduce a new variable phi and rewrite the integral as. Note that for phi equals 1 we recover the original integral. Now we proceed, integrating both sides of with respect to phi between the limits 0 and 1 yields therefore f equals f. However, we note that from the equation for f, we have f equals 2 pi, therefore the value of f at phi equals 1, which is the same as the integral we set out to compute is 2 pi. Other problems to solve. There are innumerable other integrals that can be solved quickly, using the technique of differentiation under the integral sign. For example, consider the following cases where one adds a new variable alpha. The first integral, the Dirichlet integral, is absolutely convergent for positive alpha but only conditionally convergent when alpha is 0. Therefore differentiation under the integral sign is easy to justify when alpha greater than 0. But proving that the resulting formula remains valid when alpha is 0 requires some careful work. Applications to series differentiating under the integral can also be applied to differentiating under summation, interpreting summation as counting measure. An example of an application is the fact that power series are differentiable in their radius of convergence. Popular culture. Differentiation under the integral sign is mentioned in the late physicist Richard Feynman's best-selling memoir Surely You're Joking, Mr. Feynman, where he mentions learning it from an old text, Advanced Calculus, by Frederick S. Woods while in high school. The technique was not often taught when Feynman later received his formal education in calculus and, knowing it, Feynman was able to use the technique to solve some otherwise difficult integration problems upon his arrival at graduate school at Princeton University. The direct quotation from Surely You're Joking, Mr. Feynman, regarding the method of differentiation under the integral sign is as follows. One thing I never did learn was contour integration. I had learned to do integrals by various methods shown in a book that my high school physics teacher Mr. Bader had given me. One day he told me to stay after class. Feynman, he said, you talk too much and you make too much noise. I know why. You're bored. So I'm going to give you a book. You go up there in the back, in the corner, and study this book, and when you know everything that's in this book, you can talk again. So every physics class, I paid no attention to what was going on with Pascal's law, or whatever they were doing. I was up in the back with this book, Advanced Calculus by Woods. It had Fourier series, Bessel functions, determinants, elliptic functions, all kinds of wonderful stuff that I didn't know anything about. That book also showed how to differentiate parameters under the integral sign. It's a certain operation. It turns out that's not taught very much in the universities, they don't emphasize it. But I caught on how to use that method, and I used that one damn tool again and again. So because I was self-taught using that book, one had peculiar methods of doing integrals. The result was, when guys at MIT or Princeton had trouble doing a certain integral, it was because they couldn't do it with the standard methods they had learned in school. If it was contour integration, they would have found it. If it was a simple series expansion, they would have found it. Then I'd come along and try differentiating under the integral sign, and often it worked. So I got a great reputation for doing integrals, only because my box of tools was different from everybody else's, and they had tried all their tools on it before giving the problem to me.